We shift now our discussion away from the atomistic quantum perspective of nanomaterials with its quantized phenomena to a collective thermodynamic perspective of material properties and processes. In the first section of this part of the lecture, our main focus will be on fluctuations and energy barriers. The main distinguishing feature between a process and a property is that the former describes a non-equilibrium state, while the latter one represents an equilibrium situation. To keep a process going requires a driving force. This is illustrated here with a chemical potential gradient expressed by the difference in the Gibbs free energy delta G. Nature drives, whenever possible, a system to its lowest energy state. As depicted here for a chemical reaction of a reactant with its environment, the reactant concentration reduces while the product concentration increases as long as delta G is smaller than 0. Indicated with the flux J is the fact that the process can be to part reversible, i.e. the product can be converted back in its original components. A negative Gibbs free energy change is equivalent to a larger forward flux towards the product than its reverse flux. In the language of probability, as used in statistical mechanics, the probability of a forward flux dominates the probability of the reverse flux. Keep that thought, we get back to it. Noting the reaction state diagram depicted at the bottom left, we have also included an activation barrier. This barrier is non-existing for diffusion processes that are thermally supported. Controlled chemical reactions processes, on the other hand, possess a finite activation barrier that slows the process down. Though, in the strict sense, only diffusion processes are truly spontaneous, while controlled chemical reactions are activated processes. It is, however, common to use the term spontaneous a little more loosely and consider chemical processes with negative net Gibbs free energy as spontaneous, as they can run by themselves. Over time, a process in a closed system runs out of reactants, or reaches a state at which the reverse flux matches the forward flux. At this point, the observables, that is, the concentration of both reactants and products, are invariant of time. An equilibrium state is reached. At equilibrium, the Gibbs free energy is 0. Systems that are unaffected by driving forces that result from potential imbalances exhibit behaviors that are constant in time. These time-invariant behavior are called material properties. Examples of material properties are density, speed of sound, chemical reactivity, electrical conductivity, hardness, color, heat of vaporization, to name a few from different categories. Returning to the reaction state diagram, I want to address a couple of aspects in regards to fluctuations. Fluctuations are temporal distortions or reaction attempts that are continuously occurring. In a thermal bath with molecules, we talk about uncoordinated vibrational, rotational, and translational fluctuations. In chemical reactions, we consider the resultant fluctuations that reflect the attempt of forming or breaking bonds. Depending on the system's temperature and pressure and other imposing constraints, such as shown with the reaction state diagram, fluctuations can be frozen or unsuitable. For instance, in the case of the chemical reaction described here, only energetic fluctuations that overcome the potential barriers are of value. Changing the activation barrier of the chemical reaction, by introducing a catalyst for instance, increases the specific fluctuation interval and thus the reaction rate. Constraining the system can alter the reaction diagram in all aspects. In nano-constrained systems, the free energy of the reactants and products can be different, and thus the net Gibbs free energy. The activation barrier can be raised and lowered. And finally, the fluctuation spectrum altered, in particular in regards of intensity. Comparing a macroscopic thermodynamic system containing a large number of molecules to a nanosized system with a small number of molecules as compared to Avogadro's number, we notice small versus large fluctuations in the observable. As the size of the fluctuations are on the order of 1 over square root n, where n stands for the number of molecules in the systems, large systems exhibit vanishingly small fluctuations in the values of their observables. As such, the average of the observable of a large-scale system offers equilibrium parameters. In small systems, however, fluctuations are large, and the mean values over time do poorly reflect the actual values of the observable at a given time. Noticing the increase in the fluctuation size and the decrease in the number of fluctuations, the nanoscale offers multiple opportunities to influence processes. For instance, with an increase in the fluctuation size, a process hindered on the macro scale by an activation barrier can become possible on the nanoscale. In other words, the nanoscale can provide a process catalytic environment of sort without actually adding a catalyst. This provides a wonderful opportunity, as it could offer economic and environmentally sensitive alternatives for applications that rely on rare and environmentally malignant catalysts. Also, with a substantial decrease of the number of molecules on the nanoscale, significantly fewer fluctuations can be expected. With a decreased fluctuation intensity, a slowdown in the process kinetics can be expected. This is desirable, for instance, in shape-sensitive nucleation and growth processes of nanoparticles, or to provide safer reaction conditions for otherwise violently fast processes. From this perspective, the nanoscale resembles an inhibiting-like environment. It is important to note that the catalytic and inhibiting aspect of the nanoscale are not mutually exclusive. Both of them can occur at the same time. So far we have addressed the effect and the interplay of fluctuations on properties and processes. We recognize the importance of driving forces that result from potential differences. When we come back, I will talk about how we can capitalize on fluctuations by choosing an appropriate time scale and rectifying thermal fluctuations.